Well, today we're going to be taking a look at this nano VNA. I got a couple of the screws removed for ease of disassembly. So a nano VNA, it's a network vector analyzer. And what it allows us to do is measure the reflected signals from an RF circuit. This is important because if you're measuring the characteristics of an antenna, if you get a lot of reflected power, what that means is that your antenna isn't tuned correctly. And we want to try to minimize the amount of RF power we're putting into the environment. So we want to optimize our electronics in order to do that. A few other interesting things that it can do is it can measure the frequency response of pretty much, well, any filters you put in. Basically, a filter is like a classic low pass filter, a notch filter. Um, it can help you measure the effectiveness of ferrite beads. So those are the little round things you see on the end of cords that just are kind of there for no reason. These are really nice to have because they decrease the amount of energy reflected by the circuit. And here is the bottom of this. This is honestly really disappointing. There's two shields here that I don't think I can get off with ease. Um, these soldered? They're not soldered, but they're very well clipped on. So we're not going to remove these today. But what we will do is we will have a good look at all of these ICs. So I will go ahead and look at what all these ICs do. Well, spoiler alert, I've already done this. So to give you some idea of the topology of this, or just some general the circuits on here. Right here, these little guys, U2 and all the little square ones like that are switches. So they divert the RF path to elsewhere. And then here's our main IC that does all of our glue logic. That pretty much just takes care of everything on the chip. This right here is our battery management chip. It's a standard power bank IC that does power bank stuff. Um, let's see. Well, let's hop into the data sheets on all these chips because I actually have all of them looked up, and we've already done all of the work to decipher this. Don't worry about this. This is coming up in another video. So we'll be right back. Hello. So I have the picture in front of us right here. So this one right here is our VCO synthesizer chip. That is this guy right here. This guy does a lot of the special sauce. So this is what allows us to measure the frequency response of most things. You know, if if we wanted to get into the weeds, we'd go into this chip and this chip. But this chip does a lot for this. Here's the block diagram. Okay. Our power bank IC right here. Let's go over to that. We see that I've done too many takes of this and that this is a system on chip with actually some pretty good efficiency, 93%. To see anything in the 90s these days on a nominal data sheet is a very good thing to see. A few other cool things. We have this low standby current and an integrated key. So that's good. This is a very nice chip. We're not using many of the features of it because we don't have a flashlight control. We're not doing auto detection. It is using the LEDs, but as we saw before, the battery wasn't pre-installed. It is just an 18650 though, so it's not too bad to install. Um, yeah, there's not much else to say about this chip. Um, then we go over to here. This is the RF circuit, switch circuit. This is cool because we have 4 channels that we can switch between, and there's a whole bunch of these on the chip. Um, the reason there's so many is because we need to be able to do the calibration modes. So we basically need to be able to switch the amplifier from one side to the other and do a whole bunch of other glue stuff. So that's why we have so many of these. Let's see. We have the rail-to-rail op amp, which is an interesting one. This was, let me look at my notes real quick. U304. So U304 was right here, I think. Yeah, U304. This is an interesting chip on this circuit, which I forgot to mention. I have the whole schematic. So that dual op amp is right here, which is serving as a differential amplifier and decoder chip. So I'm not gonna get into the weeds of all of this because there's a lot of switching here, and we see that there's a lot of rails going all over the place. But this is cool because we see that they're not just using, you know, they're they're doing stuff. What else is interesting on this? Yeah, realistically speaking, I've done too many takes of this and waited too long to do it, so it's kind of burned out in my memory. This is a cool chip actually. So this takes in a crystal oscillator and then is able to output nearly any frequency with very good frequency stability as well. And it's actually a pretty complicated chip because of the amount of synthesizers it needs in order to be able to do that. Here is the actual device itself. Well, this is the general version. We have the software somewhere here. I got this working today. It's actually kind of cool. It allows you to do all the functionality through a computer, which is nice. It does add in some noise because you are using a external power supply. And with this design especially, there's not really any sort of internal filtering that makes it an exceptional power supply. It's going to be using the same DC to DC converter with that power management IC. So you will get better performance with it not hooked up to a computer. But what you will see is that we can easily interact with it and we get all of this data just shot out at us really quickly. So when we're trying to see all of this, we can just see our markers right away. We don't have to fumble through a menu. This is Windows 11, and I did have to install the driver for it. This Cypress driver installer, it's a serial driver. On the website, it does say that you don't need to install this, but um, where did it go? I don't know. But anyway, I think that's about all I have for this device right now. I'll let you know if anything comes up with it.